In the realm of multi-relational graph clustering, the alignment of different views has been a cornerstone of prevailing methods. However, a pervasive presence of imbalance in real-world graphs contradicts this motivation. To address this challenge, the authors propose a novel metric, Aggregation Class Distance, ACD, to empirically quantify structural disparities among different graphs. They then introduce balanced multi-relational graph clustering, BMGC, which incorporates unsupervised dominant view mining and dual-signal guided representation learning. BMGC dynamically mines the dominant view throughout the training process, synergistically improving clustering performance with representation learning. Theoretical analysis ensures the effectiveness of dominant view mining. The authors demonstrate the superiority of BMGC through extensive experiments and in-depth analysis on real-world and synthetic datasets. The authors first highlight the importance of multi-relational graphs, which involve a set of nodes with multiple relations, in characterizing complex systems. They discuss the limitations of conventional multiview graph clustering, MVGC, methods, which often align all views to seek consistent information with the aid of a contrastive learning mechanism. This approach ignores the fact that different views in real-world data do not always carry equal significance, leading to the view imbalance phenomenon. The authors then propose ACD as a simple yet effective view evaluation metric, which takes into account both the aggregation process and the distribution of node classes. They also introduce BMGC, which integrates an unsupervised method for dominant view mining and dual-signal guided representation learning. The dominant assignment is utilized to further enhance the clustering performance. The authors underscore the primary contributions of this study, including exploring view imbalance in multi-relational graphs and designing a metric for evaluating view quality, tackling view imbalance without supervision, and conducting comprehensive experiments and in-depth analysis on real-world and synthetic datasets. The research proposes balanced multi-relational graph clustering, BMGC, to overcome view imbalance in multi-relational graphs. It begins by introducing the Aggregation Class Distance, ACD, metric to quantify structural disparities across different views. ACD evaluates structure quality based on aggregated feature distribution of node classes. The methodology involves scalable graph encoding, unsupervised dominant view mining, and co-aligned representation learning. Scalable graph encoding decouples graph propagation and dimensionality reduction to improve scalability. Unsupervised dominant view mining quantifies the discrepancy between the similarity matrices of original features and view-specific aggregated features. Co-aligned representation learning aligns the representations of other views with the dominant view using contrastive learning. The framework also incorporates a loss to ensure alignment with node features. The final loss function combines the alignment losses from both the dominant view and node features. This approach enhances clustering quality by leveraging dual signals from the dominant view and node features. The paper presents balanced multi-relational graph clustering, BMGC, a novel method for unsupervised clustering of multi-relational graphs. BMGC applies a soft assignment distribution to enhance cluster cohesion and minimizes the KL divergence between the distributions of the final representation and the soft assignment distribution. Theoretical analysis demonstrates that BMGC corresponds to the view with the maximum ACD value, ensuring effectiveness in unsupervised dominant view mining. Experimental results on real-world datasets show BMGC consistently outperforming various baselines, including the supervised method HAN, on metrics like NMI, ARI, ACC, and F1 score. The method's superiority is particularly evident in datasets like Amazon and ACM2, where it improves NMI and ARI by significant margins. BMGC's performance highlights its ability to effectively leverage the information from multiple views, addressing the imbalance issue and outperforming methods that overlook this aspect. This research paper proposes a novel approach to tackle the challenge of view imbalance in multi-relational graphs, which is prevalent in real-world datasets. The authors introduce a new metric, Aggregation Class Distance, to quantify the structural disparities among different graphs. They then propose balanced multi-relational graph clustering, BMGC, a method that dynamically mines the dominant view throughout the training process, collaborating with representation learning to enhance clustering performance. The authors conduct extensive experiments on both synthetic and real-world datasets, including MAG, Amazon, ACM, DBLP, and Yelp. The results show that BMGC consistently outperforms state-of-the-art methods, even in the presence of noisy data. The ablation study demonstrates the importance of each component in the BMGC model, including alignment with the dominant view, alignment with node features, and dominant assignment. The case study provides insights into the effectiveness of unsupervised dominant view extraction and the reliability of dynamic mining in the training process. The authors also conduct a hyperparameter analysis on the teleport probability alpha and the radius of graph propagation k, showing that the model is robust to changes in these parameters. Theoretical analysis validates the efficacy of unsupervised dominant view mining, and the experiments demonstrate the superiority of BMGC over existing methods. The results highlight the importance of addressing view imbalance in multi-relational graphs and the effectiveness of the proposed approach in achieving robust and accurate clustering results. Overall, this research contributes to the development of more accurate and robust graph clustering methods, particularly in scenarios where view imbalance is a significant challenge. The proposed approach has the potential to be applied in various domains, including social network analysis, recommender systems, and computer vision. The proposed balanced multi-relational graph clustering (BMGC) model is designed to effectively handle both homophily and heterophily in multi-relational graphs, enhancing clustering performance by leveraging the complementary information from different views. This model utilizes a novel objective function that combines reconstruction loss, contrastive learning loss, and self-training clustering loss to optimize the clustering results. The model's performance is further improved through the use of a dual-branch architecture, which facilitates the learning of view-specific and shared representations simultaneously. In the provided pages, the authors present a detailed analysis of the BMGC model, including its objective function, algorithm, and theoretical analysis. The objective function consists of three parts: a reconstruction loss that encourages the model to preserve the topological structure of the graph, a contrastive learning loss that promotes the alignment of representations across different views, and a self-training clustering loss that helps refine the clustering results during training. The algorithm pseudocode illustrates the steps involved in the BMGC model, including feature aggregation, dominant view identification, and loss calculation. The theoretical analysis section provides insights into the behavior of the BMGC model under certain data assumptions. Specifically, the authors prove that the expected difference between the aggregated features of two clusters is proportional to the difference between their mean feature vectors, which indicates the model's ability to differentiate between clusters. Additionally, they show that the variance of the aggregated features decreases with an increase in the number of hops, suggesting that the model can effectively capture long-range dependencies in the graph. The references provided include a wide range of studies on graph neural networks, multiview learning, and clustering algorithms, demonstrating the breadth of research that the BMGC model builds upon. These references highlight various techniques for handling multi-relational graphs, such as using graph autoencoders, contrastive learning, and dual-branch architectures, as well as the importance of preserving both homophily and heterophily in clustering tasks. This research focuses on balanced multi-relational graph clustering, proposing a novel metric called average community distance, ACD, to measure the relevance of graph structure to downstream tasks. The authors demonstrate the effectiveness of ACD by generating synthetic datasets using the multi-relational CSBM model, which allows for controlling the proportion of contributions from graph structure and node features. The synthetic datasets are generated by introducing perturbations to the initial graph structures, resulting in imbalanced multi-relational graphs. The authors then use a linear layer as a classifier for view-specific features and show that ACD is positively correlated with classification accuracy, empirically proving its effectiveness. In addition, the authors employ 5 publicly available real-world benchmark datasets and a large-scale dataset, including citation networks, ACM, ACM2, DBLP, and MAG, and review networks, Yelp and Amazon. They provide a brief introduction to several baseline methods, including Han, VGAE, DGI, O2MAC, DMGI, MVAGC, HDMI, MCGC, MGDCR, and DUALGR, which are not described in the main paper due to space constraints. The mathematical derivations on page 11 show the expression for the expectation of XX15, 15, which is a crucial component in the proof of the ACD metric. The authors posit that the magnitude of parallel mu squared mu far exceeds df sigma squared, and they use omega, sigma squared, to denote the sum of terms containing sigma squared, highlighting that this term has a negligible magnitude in comparison. Overall, this research contributes to the development of a reliable and effective metric for measuring the relevance of graph structure to downstream tasks, and it provides a comprehensive evaluation of the proposed ACD metric on both synthetic and real-world datasets. Balanced multi-relational graph clustering, presented at MM24, is a novel approach that integrates two key components: a dual-label guided graph refinement module and a graph encoder module. This method aims to leverage the strengths of both components in order to enhance clustering performance on multi-relational graphs. The proposed approach is compared against two existing methods, DMG and BTGF. DMG is an unsupervised multiplex graph representation learning method that disentangles comprehensive and clear common information while capturing more complementary and less noisy private information. On the other hand, BTGF is a multi-relational clustering method with a novel graph filter motivated by the theoretical analysis of Barlow twins, which makes the inner product positive semi-definite to upper bound Barlow twins. The dual-label guided graph refinement module utilizes both node and edge labels to refine the graph structure iteratively. It optimizes the graph structure by adjusting the edge weights based on the similarity between node labels and edge labels, enhancing the clustering performance. The graph encoder module, on the other hand, uses a neural network to learn the node representations that preserve the graph structure and node attributes. The proposed method outperforms DMG and BTGF in various clustering metrics such as modularity, conductance, and clustering coefficient. The experiments demonstrate that the proposed method can effectively identify clusters in multi-relational graphs, even when dealing with noisy or incomplete data. A significant contribution of this work lies in its ability to balance the influence of different types of relationships within the graph, leading to more accurate clustering results. This is achieved through a novel objective function that encourages the formation of dense clusters while penalizing the creation of isolated nodes. In conclusion, the proposed balanced multi-relational graph clustering method offers a promising approach for analyzing complex networks. By integrating a dual-label guided graph refinement module and a graph encoder module, it effectively balances the influence of different types of relationships within the graph, leading to improved clustering performance compared to existing methods like DMG and BTGF.